Yeah, but before starting today's session, I would like to share one story related to Bode plots. So, yeah, I have done my BTech in from 2017 to 2021, and I had taken the control systems course in 2019. Okay, so the professor who had taught me controls have taught the Bode plots really well. So I used to think that I am pretty good at Bode plots, and I somehow like Bode plots because it is very interesting and fascinating to me. So I thought that I'm pretty good at body plots and I'm very much confident in body plots. Then later in 2020 December, I was doing one course, power electronics course, Coursera course by Professor Dragan Maximovich and Robert Erickson. And when the Bode plots was about to start, he, mentioned something like a disclaimer saying that you might have already done Bode plots in your UG or in your PG, whoever is attending this course. But he mentioned that please go through these lectures in the way that we are teaching, means Professor Robert Erickson was teaching. And he mentioned that this will be slightly different from what we might have learned in the UG and PG. And he mentioned that this will be very insightful. He will give a different flavor or a different perspective to body plots that people might not have gotten in their earlier courses, UG or maybe PG. So then I thought in my mind, because I was confident in body plots, that this professor say like this, so why don't I skip the lectures and then directly solve the assignment? Okay, and then I have solved the assignment and I could not solve the assignment. Then I realized that I am not pretty strong in body plots, and then I started going through the lectures. And even this time, I was, little bit, overconfident, and I thought I can skip the lectures rather than going at normal pace, and I have done it in a very hurry way, and I have not done it well. And then I started solving the assignment and tried to solve and obtain the answers and submitted, and only to see all of my answers are wrong. So now, then I got actually humbled that I do not know fully. Then I have accepted it, and then I started going through the lectures point by point, taking the notes. And then I actually got a different perspective, which I never had before. And then once I solved the assignment, I was now confident with the border plots in the way he has taught, and then I was able to solve the assignment. So what I wanted to share is like that was one experience where it has taught me that we have to be open, even though we know, even though we have done it in the past. We should be open to learn more. Like if I am closing my mind saying that I already know, I don't want to know something new, then we can never learn. But in the same way, if we, even if we know, if we are open to see, maybe we'll learn something new. And if we go through something, some lecture, we might always learn a single point, even though if it is a single point, we'll learn something new. So what I wanted to say is we have to be open in that way, and accept that we learn only less, and then we have to learn something more. Only in that way we can let the knowledge enter our mind, and we can learn new things. If we close that door by thinking that we know everything, then we'll not be able to learn something new, because we are in that bubble thinking that we know everything. But only if we come outside the bubble, we know what all we can learn. Yeah, so that being said, welcome back everyone. We are in the week 6 problem solving session of the NPTEL course Control Engineering, and week 6 is about frequency response, Nyquist plots as well as Bode plots. I am Teja Golla, a 5th year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen and let me know when you can see my screen. Can you see my screen? Can anyone please confirm?
I can.
Okay, okay. Yeah, I wish I could teach in detail because frequency response is such an important topic in control systems. But the concepts that sir has covered is so vast that I may not be able to teach everything from scratch, but I'll try to touch upon. But I'll not be able to teach everything in detail because the time is limited. We also have to solve problems. I'll also be showing some MATLAB simulations, and I'll share the code by uploading it to the Google Drive, and I'll share the Google Drive link. So yeah, forgive me for that because I'll not be able to spend too much time in Nyquist as well as Bode Plot and then teach them in detail within 2 hours. That is impossible, but I'll try to cover as much as possible, and I'll try to clarify your doubts, and we can have a better insight. And then I'll try to correlate what we are doing analytically with hand versus using MATLAB. So we have to learn both, because we also need to know how to, use the MATLAB toolbox or whatever toolbox, so that it will be helpful in the future when the dynamics increase. So why is frequency response very important? So the first reason is time domain response, or whatever we have done in the time domain. So in the case of time domain, whatever we have done in the time domain, so there is one issue. What is that issue? If you see, we have considered till second order, right? We have considered till second order, and then in the second order we could relate the natural frequency, damping frequency, as well as eta. So now what if the order of the system increases, then the complexity increases, and we may not be able to solve everything in time domain. It will become complex. So the main issue in the time domain is it will become complex. Complexity increases as the order of the system increases, as the order of the system increases. So it is not so straightforward. Say I have given you a fourth order system, and I have given step response and asked you to find the output. It will become cumbersome, right? We will not be able to understand how certain variables in the system are affecting the response, or what will affect what. Say if I want more overshoot, less overshoot, what needs to be changed so that my output response will look in the way we want. So that insight is missing, or that understanding is missing, so that we cannot correlate between something in the system to the output. So that will be missing in the time domain. So this will motivate us to move to frequency domain, because in frequency domain we can solve for nth order. We can check the stability, we can see how the system is performing, and then we'll try to relate some frequency terms with the time domain. So we can see, say, if bandwidth is high, the response will be faster. If phase margin is good, then the damping will be good. So this kind of correlation we'll be doing, and frequency response is easier in terms of physical understanding, or you can have the visualization. So you'll get an insight that how the frequency response is looking, or what is changing when the order is changing. So you can relate poles and zeros in terms of response. So that's why we use frequency response. So that's why we go to frequency domain. So this is frequency domain. It will be easy to understand or study about higher order systems. Higher order systems. So one advantage of the LTI is, if you see, let me consider one system. So let me draw one system real quick. So I'm considering one system, say G of S, and input side I have U of S and Y of S. So in time domain it will be U of t, as well as here it will be Y of t. So the advantage of frequency response is, say we are exciting it with an input, say A sine omega t. Okay, I'm exciting it with A sine omega t. And again, this is under the assumption that this is LTI system. So this is applicable only for LTI system. So if my input is A sine omega t, I'll get some B, not A, some gain B. So it will be B sine omega t plus phi. So the frequency of the input will not vary. So the frequency of the input as well as the output will remain the same. However, there will be a phase shift, and also there will be change in the amplitude. So this is the biggest advantage of using frequency, because we know that only either the magnitude is changing or the phase is changing. So now what we are doing is, we are only checking the input to output magnitude change as well as the phase change. So now what we are doing is, we are checking from the input to output, we are checking how will be the phase, how will be the magnitude. So now using this magnitude as well as phase, now we are trying to understand the system. So system this system can be studied by understanding about this as well as this. And we know that only difference between the input and output is magnitude as well as phase. So these two are the only things that are changing from input to output. And only they are changing. So now by understanding the magnitude, how the magnitude has changed or how the phase has changed, we'll try to understand what are there in the system or how the system is responding, and then we'll try to study the system based on this input as well as output. Can anyone tell me why do we use only sine? Like why not any other? Like why do we use only sinusoid input? Why not square input or why not triangular input? Anyone? Any guesses? No guesses? Okay. So the like as I said, the one of the most important thing is the frequency is not varying from input to output. So maybe I'll mark it. So the important is frequency is not changing. Only the time period is sorry, amplitude and phase is changing. So the frequency remains the same. Okay. And if you consider sine, it's a single frequency component, right? It has only omega. So we are exciting it with a single frequency component, and the output is also single frequency, but phase shifted and amplitude has changed. So what if I give a step input? Step input is not a single frequency, right? Step input has, I can consider it as a Fourier series, and I can consider, infinite series of different frequencies. So now each frequency will have amplitude change as well as phase change. So the square input that I have given will not look like a square input because each frequency will have a different amplitude change and different phase change. And when you combine all the infinite series, it might have an abnormal shape and we will not be able to make out anything from that. So that's why we consider single frequency component. So we consider sine omega t because phase is zero. Cos omega t can also be considered, but it is like sine with a phase shift, right? So sine starts from zero, so that's why we consider sine. But we are very free, like very free to consider cos as well, any single frequency component. So we are considering single frequency and then comparing its amplitude, input to output versus its phase. So that is the reason that why frequency response is very famous, because we can get the input output correlation by exciting it with a single frequency component. And now we will be discussing about different type of plots, and how those plots will help us to understand regarding the closed loop stability, or their frequency response, gain margin, phase margin. So this is something I would like to explain before we dive into polar plots, Nyquist plots, and as well as the Bode plots, like why frequency response is very important. Is this clear, everyone? If you have any doubts, you can ask. I'm just giving some little insight, like why we are learning frequency response and why it is important. Any doubts until this point? Revant, Niladri, Ramesh? Okay, I think they have replied. Yes, sir, clear. Okay. So now we'll move to each of today's topic, starting with one system, and we are asked to plot. Okay. So now basically what we are doing is we will be checking again. We will be sweeping the frequency. We'll sweep the frequency from certain range to certain range and see how the magnitude and phase is varying. So that is one way to draw the polar plot and see how the system is varying. So here we have a negative feedback system with the loop transfer function given as g of s. So this is the g of s, and consider it as a unity negative feedback. So h of s is 1. So now we have g of s as 1 by 1 plus s into 1 plus 5s. Okay. So one more thing, this frequency response that we are talking, say I have excited it with a sine frequency, right? So a sine omega t, it will have some transient, and at steady state it will be converging to sine. So basically we are talking about the steady state behavior, not the transient behavior. So this is steady state behavior that we are discussing. So we'll let the output settle, then it will have single frequency. Of course there will be transient. So once it settles, then we are talking about that magnitude as well as phase. So this is basically steady state behavior. So now if you see here, usually what is s? S is sigma plus j omega, right? So in this sigma corresponds to the transient, like it is mainly involved in the transient terms, and omega is corresponding to the steady state. So when we are saying uh, that we are only interested about the steady state, usually that time the sigma terms have died down. So if we have exponential terms e to the power sigma t, or e to the power minus 2t, e to the power minus 3t, they will die down at steady state, right? So basically sigma will vanish. So at steady state we'll be considering, so at steady state we will be basically considering s is equals to j omega. So basically this is a steady state. So that's why it should be very clear why we consider only s equals to j omega, and then we'll see omega varying from certain frequencies to certain frequencies, and then we'll try to understand. Okay. So now coming to our first problem, which is polar plot. So whenever we have given in g of s, you know what we have to do? We have to first write the expression in g of j omega. So we'll get s is replaced by j omega. So we have 1 by 1 plus j omega into 1 plus 5 j omega. So from here, I can calculate the magnitude of g j omega. So how to calculate the magnitude? We'll take the magnitude individually. So it will be 1 plus, in the bracket we'll have 1 plus omega square, and then 1 plus 25 omega square. Okay. And then what will be the phase of g j omega? Because it is in the denominator, we'll have a negative sign. So it will be minus tan inverse. The first one will be omega, because they're in the product, phase will be addition, but because they're in the denominator, we'll have a minus sign. So tan inverse omega, tan inverse 5 omega. So is this clear how we have obtained the magnitude and phase? Because as I have mentioned, only the magnitude as well as phase is changing. So that's why we are only interested in the magnitude and phase, and based on that we'll try to understand the functionality of the system. So that is what exactly we are doing here. So people who have joined late, I'll just quickly summarize so that you will not miss out anything. So we have started with frequency response. Why frequency response? Because time domain can become complex as the order of the system increases, and we'll not be able to correlate exactly how the output response will, vary, or whatever changes that we are making, how it is going to reflect on the output. So that's why we choose frequency domain. It will be easy to study about the higher order systems. And one important aspect of the LTS system is if you excite it with a single frequency component, output also will have the same frequency, but only amplitude and phase will vary. So that's why we are only studying about the magnitude and phase, because the frequency remains same and only these things are varying from the input to output. And by studying magnitude as well as phase, now I am able to understand the dynamics of the system, and I can also comment on the stability using Nyquist plot as well as Bode plot. And it's again steady state behavior. This will reach to certain sign only at the steady state, but there will be a transient. During the transient, it will have e to the power sigma t term, which will eventually die down. So at steady state, we'll only consider s equal to j omega, because sigma terms are vanished. So that's why whenever we are trying to plot this, we'll only consider s equals to j omega, because it's a steady state phenomena, not transient. So we'll let the system settle down, and then we are considering its magnitude as well as phase. So did you understand how we are getting this magnitude as well as phase? Yeah. If you can't, talk, then I think it would be good if you mention in the chat so that I can get a feedback. Okay. So Ravan says yes, sir. So if you have any doubts, please stop me at this point, else I'll continue how to draw this polar plot. So I have asked, draw the polar plot omega equals to 0 to omega equals to infinity. So at omega equals to 0, let us see the magnitude, and let us see the omega equals to 0. Let us see the magnitude and let us see the phase. So omega equals to 0 means what it will be? Omega, we have to substitute 0. So mod of g omega, what is the value of mod of g omega and angle gj omega? Anyone? Omega equals to 0. Can you mention the answer in the chat box? And also, if you have calculated that, let me know. Omega tending to infinite, what will be the magnitude of gj omega and angle of gj omega? So we have to substitute omega equals to 0 in this magnitude expression as well as this angle expression, and then obtain this. So can anyone solve? If we substitute omega equals to 0, what will be the magnitude? Anyone? So if I substitute omega equals to 0, this term and this term will vanish and magnitude will become 1, right? So magnitude of gj omega will become 1. And phase will be tan inverse 0 means 0 and 0 minus 0 is 0. So it is 1 angle 0. So from this I will get it is basically 1 angle 0 degrees. Now coming to omega tending to infinite, if the omega is tending to infinite and the denominator goes to infinite, magnitude will be tending to 0. And what will be the angle? Tan inverse infinite is what? Pi by 2. Tan inverse 5 into infinite again infinite, it is pi by 2. So minus pi by 2 minus pi by 2, it is minus pi or minus 180 degrees. So it is considered as 0 angle minus 180 degrees. So in the polar plot, we have real axis as well as imaginary axis. So let me draw the axis first. So we have real axis, we have imaginary axis. So we have the axis here. And then whenever we are plotting, right, we'll start from omega equals to 0. So omega equals to 0. So this is basically real. This is basically real axis and this is basically imaginary axis. So we are starting with 1 angle 0. So magnitude is 1, angle is 0. So basically we are starting, say this is 1 angle 0 and this is corresponding to omega equals to 0. As we move to omega towards infinite, what is happening? We are moving to 0 angle minus 180 degrees. So 0 angle minus 180 degrees is, it is close to 0, but angle is minus 180 degrees. So just around this point. So how are we going from this point to this point? If you see, I am considering omega equals to 0 and it is 1 angle 0. Say omega is some positive value. Say omega is some 10 or 20 or little bit higher value. Then what happens? Magnitude is what? Magnitude is some constant value. But what about phase? Phase is minus tan inverse of some positive value minus tan inverse of some positive value. So phase is always negative. So what does phase negative meaning? It is always in quadrant 2 or quadrant 4. So basically it is moving from omega equals to 0 to omega tending to infinite with always negative angle. So it is always in Q3 and Q4. So we can draw something like this. So it is going in this direction. So we are not bothered about the shape. We are only speaking how it is going. So you may ask why it is not going in the Q4 itself. Because I got 0 angle minus 180 degrees. So it is on the left side, right? So it is just left side of the origin. So it is coming from this angle. So it has to cross the j omega axis at some point of time and it is going in this direction. So we have started from omega equals to 0 and we are tending at omega equal to infinite. So for each we have to calculate magnitude as well as phase, and based on this magnitude as well as phase we know the location, and we have to in between also calculate certain values if we are not sure how it is going. If I have considered some positive value, say 10 or omega equals to 10, I found out that the phase is negative, which means it is in the quadrant 2 or 4, but it has some value. So it is moving from here to here, but it is coming from the left side. So that's why I have made sure that it is crossing the imaginary axis. So this is how we get this plot. Is this clear? I have considered one simple example how to, vary omega from 0 to infinite, and then how we are plotting the magnitude as well as phase. If you have any queries, please let me know. If you are also not clear, let me know. I'll try to re-explain it. Uh, if you don't respond, it will be difficult whether I have to re-explain or go to the next one. So please let me know. Yes, sir. So Nilatri, it is clear, right, for you? Niladri? And what about others? Revant also says yes, sir. Okay. So now that we have plotted, I'll also show a MATLAB simulation of the same. Say I have a MATLAB. I will again give these codes to you so that you can also play with the codes and try to understand how things are varying. So I have defined, as I have told, CLC will clear this command window, CLC, and clear will, clear this workspace, and close all will close if there are any plots. And if I press CLC, it will clear the command window. I have defined S as a transfer function S, which means it is just S. Okay. So now S variable is defined as transfer function S. Okay. So this is a transfer function. Now I am considering G as 1 by S into S plus 1, the example I have considered earlier. Now my example is 1 plus S into 1 plus 5S. So I'll consider denominator. So brackets should be very careful. I'm considering 1 plus S multiplied by 1 plus 5 star S. Okay. And then I'm displaying so that I'll see whether whatever I have typed is correct or wrong. So let me run this. So it is, if I multiply by 5, it is 1 by S plus 1 into 5S plus 1. So they basically normalized it. Okay. So this is the transfer function that I have given, and I'm plotting the Nyquist plot. So Nyquist plot will plot from omega equals to minus infinite to plus infinite. But since we are plotting only half of that, we will get only the bottom side, and the top side is when you move from omega minus infinite to again 0. So if you see, this is the plot. So it is starting from this point, and this is the imaginary axis. At 0 it is the imaginary axis, so it is going from this point in quadrant 3 and 4, and then again it is going to 0. Now if we draw one of the wing or the branch, the other one will be the mirror image of this. So it will be becoming very simpler. Once we have plotted this, it will be the mirror image. So is this clear? If you have any doubts, please stop at this point, else it will, doubts will pile up, and then the concept will become unclear. So that is like very important. Your doubts has to be cleared. The session is for that. If you have doubts, I'll try to explain multiple times, but don't stay calm. This is a simple code. We are defining a transfer function, and we are drawing the Nyquist plot, and see whether whatever we are getting is correct or wrong. Is this clear? So this is the direction it is showing. We are starting from this point. So this point is 1 and angle 0, and from there it is going to 0 minus 180 degrees. 0 angle minus 180 degrees. So in that way it is moving. Any doubts until this point? Again, I'll share this MATLAB codes as well so that you can check or play with them during your leisure time. And you can also cross check whether whatever you are drawing is correct or wrong. Uh, any doubts until this point? Else I'll move to the Nyquist stability criterion. Revan says clear, sir. What about others? And I always recommend you to solve more problems whenever you are having doubts, so that your doubts will be clarified as you solve more. So yeah, Niladri says clear. Ramesh also says clear. So coming to the next topic, which is the Nyquist stability criterion. Again, as I have mentioned, because the time is limited, we'll not be able to, either solve the problems or thoroughly discuss regarding the concept. So I'll try to uh, teach whatever is needed, not entirely from scratch and in detail, but I will also try to solve problems and show MATLAB, so that there will be balance in all three aspects. One is the concept learning, one is problem solving, and other one is MATLAB simulation. But in this way, I'll not be able to cover the concept in detail, given the time is limited to 2 hours. So yeah, please forgive me for that. So I'm starting the Nyquist stability criterion. So what does Nyquist stability criterion do? So it will try to let us know the stability of the closed loop by plotting the Nyquist plot of the loop transfer function. Say we have GH. I'll give very quick explanation, and then we'll move to the plots. I have considered few example. So this is the system that we have. So we are trying to check the closed loop poles of this system. So that will define the stability. Basically, we are trying to understand the stability of the system. Okay. So how do we check the stability? We'll check by the closed loop poles, right? Closed loop poles. So how do we check the closed loop? So for that, we'll draw the Nyquist plot of GH. So the Nyquist plot of GH, which is like a loop transfer function. So G of S, H of S. So why Nyquist is very important, or the advantage is we are trying to plot something of the loop transfer function or the open loop transfer function, and then it will give us the information about the closed loop poles without even calculating the closed loop transfer function. That is one of the advantage of Nyquist, because we are not even discussing about the closed loop transfer function or those equations, but we are only dealing with G of S, H of S, and then it will let us correlate from G of S, H of S to the closed loop poles. So that's why Nyquist plot is famous, and also it is very accurate. In Bode plot, there are some disadvantages, that in certain cases it will not be able to capture the stability, whereas the Nyquist plot will be always able to capture the stability. And now we will check why is it so. So if you consider the closed loop transfer function, say I'm considering G closed loop of S, we will have G of S by 1 plus G of S H of S. So now we are trying to check how many times G of S H of S will enclose minus 1. So basically in this Nyquist plot, what we are trying to check is, we are trying to check how many times G of S H of S is encircling minus 1. That is kind of checking how many times the, like, it is related to this characteristic equation, right? So this is the characteristic equation. So we are correlating with the characteristic equation. So based on this characteristic equation, we'll try to get how many number of poles this has, right? So the zeros of 1 plus GS HS. So one important aspect again here is the zeros of 1 plus G of S H of S is nothing but the poles of the closed loop transfer function, right? Because it is in the denominator. So the numerator of this is the denominator of that. So my aim is to find the closed loop poles, right? So in order to find this guy, we are not directly finding that guy. Instead of that, we are finding this guy. So we are trying to find the zeros of 1 plus G of S H of S, right? So this is my overall aim. So we are trying to find this, and then now that gives me the closed loop poles, so that I can comment on the stability. So this is how the Nyquist plot is working. Again, there are details like contours, mapping, which I'm trying to skip because of the lack of time. But this is the overall idea. We are trying to relate the stability of the closed loop. For that, we need to have an idea of the closed loop poles, how many of them are on the right hand side, how many of them are on the left hand side. For that, we'll use the Nyquist plot of G of S, H of S, because if we get the zeros of this 1 plus G of S, H of S, then we'll are basically getting the poles. So if I draw this Nyquist plot, and Nyquist plot will give us the information of these zeros without even actually calculating, but by drawing the plot. From there, we'll get the zeros of 1 plus G of S, H of S, which will anyways give me the poles of closed loop. So the overall aim is to find the number of poles of the, like number of RHP poles of closed loop transfer function by plotting the Nyquist. So the Nyquist is just mapping this G of S, H of S to the closed loop. So that is the mapping that it is doing. Again, I'm talking on the surface level, not too much technical. This is the overall idea. Is that clear? Okay, if you have any doubts, you please mention. Raymond says yes, sir. Okay. So now what we are doing is, we are only interested in the right half zeros, right? So basically, yeah, Niladri also says yes, sir. So we are checking the open loop RHP poles. We are considering that region, and we are seeing how many closed loop poles are there. So basically, we are, if I draw the imaginary plane and the real plane of S domain. So basically, we are considering only this region, and then we'll map. So this is in the S domain. We'll map this into g of s h of s. Okay, we'll do g of s h of s, and then we will see the -1 point, how many times it encircles. So basically, we can consider this as infinite semicircle, and then we can go in the clockwise direction. So clockwise direction means we'll start at this point 0, and then we'll go to this infinite angle 90 degrees, and then from there we'll go to infinite angle 0 degrees, and then from there we'll go to infinite angle -90 degrees, and then we'll come back to 0. Now we will see in this way, if we are moving in this contour, this is called contour, and we are only interested on the RHPs, because that corresponds to the unstable poles in the closed loop, right? So if this is the region that I'm considering, and for this region, if I'm trying to draw the Nyquist plot and see how many times this is encircling -1. So by drawing this Nyquist plot and seeing how many times it is encircling this -1, we'll try to get the zeros of 1 plus g of s h of s, which are also the poles of closed loop of S. So this is the overall idea. And then the Nyquist criterion says n equal to p minus z. So this is very important. Just an announcement, the time is less than a minute. So if this meeting ends, kindly join back. So this is the criteria. I'll explain once we come back how to use this and how does it give the closed loop right RHP poles, which will be used to comment on the stability. If you have any doubts, you can ask me. Once we come back, I'll explain what is N, what is P, what is Z, and then we'll solve few problems to understand the concept. Any doubts until this point, anyone? Yeah. So here N is equals to number of encirclements of -1 in counterclockwise direction. And P corresponds to open loop poles. Open loop RHP poles, because we are considering the right hand side, right? And then here Z corresponds to the RHP zeros of 1 plus g of s h of s. So basically, the Nyquist is letting us to draw the Nyquist plot of loop transfer function and having an idea of the open loop poles of the loop transfer function, and it will let us calculate z, which is the RHP zeros of 1 plus g of s h of s. Zeros of 1 plus g of s h of s is poles of closed loop. So if my z is 1, one pole on the right hand side, which means system is unstable. So we have to get z equals to 0, which means system is stable. So this is the advantage of Nyquist. It will let us correlate the open loop system with the closed loop. Okay, so that is the advantage of the Nyquist. And here we are moving in the clockwise direction. And if we are getting -1 encirclement in clockwise direction, it means n is -1. If we are, this is -1 is the point. Okay, so if we are moving 2 times in counterclockwise, then n will be 2, else n will be -2. So that's how we are trying to understand this. Maybe once we solve the problem, then you will understand what is N, what is P, what is Z. Okay. So if you have any doubts regarding the definition, you can ask me. Once we solve one problem, I think then you will be able to understand uh, the application, how to apply and how to solve. I'll also be parallelly showing the MATLAB simulation, so we can correlate with the simulation as well. So should we solve one problem, or do you have any queries?
Sir, what is the difference between enclosed and encircled?
Sorry.
What is the difference between enclosed and encircled?
Both are same. Encirclement is like circling it, yeah. Encircle means it is covering in a circle. Enclosed also it is inside. It is inside that. But circle means it should go in a circle. Once we see it, it will go around the -1 point. Enclosed means it is within that. But both corresponds to same thing, because here the diagram is moving from omega equals to minus infinite to 0 to. So if we go from in this direction, how it is going around the minus 1, whether it is circling around the minus 1.
Okay, thank you.
Yeah. So let us start with this problem. Again, we are informed, or we have discussed thoroughly, that we'll start with j omega only. So first let us consider this g of j omega. And then whenever there is 0, right? So we can't calculate the value at 0. So we'll consider one small circle around the 0. So first let me draw the contour that we want to understand. Then we'll draw the Nyquist plot. So first question, how many RHP poles are there? So this is the equation, right? So let us calculate this. So how many RHP poles in G of S? Anyone? RHP poles, excluding 0, which is on the imaginary axis. Minus 1 is on RHP or LHP? One. Which one? Ramesh says 1. What about others? How many RHP poles? Right hand side on the means positive pole. Excluding 0. 0 is on the imaginary axis, so we are not considering it. We are only considering RHP poles. So everyone says 1, but it is 0, right? S equals to minus 1 is on the left hand side, not on the right hand side. I said excluding 0 because 0 is on the imaginary axis. Not clear? Or 1 is at 0, 1 is at minus 1. So excluding 0, only minus 1 is on the also LHP side. So there are no poles on the RHP side, right? So basically P equals to 0, right? Basically P is equals to 0. Number of open loop poles on the right hand side. 0, right? There are no poles on the right hand side. Getting it?
Yes, sir.
Yeah. So now we have to travel through this contour and then calculate it, how the plot is looking like. So we are considering the S plot. We are considering the S plot. So we'll skip this 0, consider one small circle. We'll skip this 0 and we'll go to infinite, and then we'll cover all this, and we'll cover all this infinite area, and then we'll come back. So we are going in this direction. Okay. So we can start at any point. So I want to start at this point. Okay. I want to start at this point and I want to go to this point. First of all, first I'll consider the small one, then I can come back to the bigger one. So when we are moving through this point, how the plot looks like, that is what we are trying to draw, which is the Nyquist plot. So let me draw. So this is the magnitude which has both magnitude and phase information. Okay, so this is how okay, and we are interested in the minus 1 point. So we are interested in the minus 1 point, and this is the real axis. This is the imaginary axis. So when we are considering the small circle, I will consider the frequency omega to be epsilon into e to the power j theta. And what are the condition? Epsilon is tending to 0 and theta is moving from minus pi by 2 to pi by 2, or basically let me calculate minus 90 degrees to 90 degrees. So because I'm only considering the right hand side, I'm only interested in the right hand side. So in this case, how is my magnitude as well as phase is varying? So that is the question. So we can substitute this j epsilon into e to the power j theta in g of this. So I can get k by epsilon into e to the power j theta, k by, so I'll get k by epsilon into e to the power j theta into e to the power, sorry, epsilon into e to the power j theta minus 1. Epsilon into e to the power j theta plus 1. So if you see, this value is very small. So I can neglect this and I can consider 1 to be much, much bigger. So I can consider the denominator, the summation part is 1. So now from this I will get k by epsilon into e to the power j theta, like a simplified one. We are trying to approximate it and then see. So now if I consider epsilon to be 0 angle minus 90 degrees. So if I consider 0 angle minus 90 degrees, then I will get infinite angle 90 degrees, right? So I can simplify this as, further simplify this as k by epsilon into e to the power minus j theta. So basically I'm considering this right hand side of the S region and seeing how many times it is enclosing this minus 1. So first I have started from this point, which is 0 angle minus 90 degrees. So let me write. So this is 0 angle minus 90 degrees. This is 0 angle plus 90 degrees. And then we'll move to infinite angle 0 degrees, infinite angle 90 degrees. This is infinite angle 0 degrees. This is infinite angle minus 90 degrees. Then we'll plot it and see how many times it is enclosing. So if I start from 0 angle 90 minus 90, it is infinite angle 0. And then if I calculate 0 angle 0 degrees, then it is infinite angle 0 degrees. And then if I consider 0 angle plus 90 degrees, then it is going infinite angle minus 90 degrees. Basically, I have gone from 0 angle minus 90, then this point is 0 angle 0, and then 0 angle 90. So in this small region, if I'm moving, how is this plot moving? So one is infinite angle 0. So I can start from this point. I can start from infinite angle 90, means it is on the y-axis infinite. Then we are moving to infinite angle 0. Then we are coming to infinite minus 90 degrees. So during that region, my contour will move in this direction. Is that clear, everyone? I have considered first the small region, then the large region. Clear, everyone? I have considered first 0 angle minus 90, 0 angle 0, and then 0 angle 90. So in this small circle, if I am moving from here to here, I am moving from here to here on the Nyquist plot. So everyone says yes, sir. Now what I will do is I'll consider a bigger circle, infinite angle 90, infinite angle 0, infinite angle minus 90. So for smaller, I have considered epsilon. So for the larger circle, I'll consider r. Okay, I'll consider r into e to the power j theta, where r is tending to infinite and theta is tending again from minus 90 degrees to 90 degrees. So now if I calculate, I'll get k by r into e to the power j theta into r into e to the power j theta plus 1. Now r is so big, infinite, that plus 1 can be neglected, because r into e to the power j theta plus 1 is nothing but r into e to the power j theta, because its value is so big. Now if you make that approximation, I'll get k by r square into e to the power minus j 2 theta. Is that clear? Because 1 is approximated. Here, this is approximated because it is small. Here, 1 is approximated because r is tending to infinite. Is that clear? Now I'll consider these 3 points: infinite angle 90, infinite angle 0, infinite angle minus 90. Again, I think it would be good if I write it here, which is corresponding to what? So say this is my point 1, then point 2, then point 3, then point 4, then point 5, then point 6. So point 1 corresponds to 0 angle 90. For 0 angle minus 90, I got infinite angle 90. So this is my point 1. This is my point 2. This is my point 3. So I have gone from 1 to 3. Now I'll do 4, 5, 6, and then it will be closed. So 4 is what? Infinite angle 90 degrees. So for infinite angle 90 degrees, I will be getting 0 angle minus 180 degrees. And for infinite angle 0, I'll be getting 0 angle 0 degrees. And for infinite angle 90 degrees. So if my R is infinite and angle is minus 90 degrees, I will be getting 0 angle 180 degrees. Right. So now I have gone from point 1 to 3. Now I'll go to 4. Point is infinite angle 90. So I am going 0 angle minus 180 degrees. So the point is basically here. So I'll go to this point. Okay. And then I will go to infinite angle 0, which is also 0 angle 0. So that point is also here, almost here. And infinite angle minus 90, that is also 0 angle 180 degrees. So all are close to each other. And from 0 angle 180 degrees, which is infinite angle minus 180 degrees. So all my 3, 4, 5 points are here only basically. So we are going in this direction. So from 3, we have gone to 4, 5, 6. So all my 4, 5, 6 are here only. 4, 5, 6 all are located at origin. And then if I see again from 6, if I'm going to 1, then it will go to in this direction. Is this clear, or I'll try to explain again? Is this clear? This is epsilon e to the power j theta, or I can say epsilon angle theta. And this is r angle theta. Okay, so I'll try to explain once again so that it will be clear. What is happening is we are trying to correlate the open loop poles. Okay, and then this region we are trying to see how it is correlating in the Nyquist plot, and then we have to see how many times it is encircling -1. So it should encircle means it should go one circle around it. Okay. Then based on that, we'll calculate Z, which is the RHP zeros of 1 plus G of S, H of S, which are the poles of the closed loop transfer function. So that will give us the stability. So for this case, P equals to 0. Again, on the imaginary axis, we are not considering RHP, but it is on the imaginary axis. So P is equals to 0. So, and I cannot consider S equals to 0 also because there is a pole here, right? There is a pole here and I cannot consider. So I have considered one small circle around it so that I will not touch that point. And I have started from 1, gone to 2, gone to 3, gone to 4, gone to 5, gone to 6. And then see, I am seeing how I am traversing in this direction. So one is what? 0 angle minus 90 degrees. For 0 angle minus 90 degrees, I got magnitude infinite angle 90. So it is at infinite angle 90. For 0 angle 0, I got infinite angle 0, which is on the real axis on the right side. For 0 angle 90 degrees, I got infinite minus 90 degrees, which is on the negative imaginary axis. And for 4, 5 as well as 6, I got 0 angle minus 180, 0 angle 0, 0 angle 180, which is very close to 0. So I am considering almost everything at the same point because one is on the left side, one is on the right side. So it is more or less same. So 4, 5, 6 are here. So from 3, I am going to here, 4, 5, 6 are here. And if I am going from 6 to 1 again, then I'm moving from here to here. So this is the overall diagram of this G of S, H of S Nyquist plot. Now I have to see, because P equals to 0, I have to see N, number of encirclements of -1 in the clockwise direction. So is it enclosing -1? So -1 is completely outside. So we got P is equals to 0. So we have P is equals to 0 and number of encirclements is equals to 0. So N equal to P minus Z implies Z equals to 0. So the RHP zeros of 1 plus G of S, H of S are 0, which means closed loop poles on the right hand side are 0. So 0 closed loop RHP poles. So this corresponds to 0 closed loop RHP poles. So with this, we can say that system is stable. So without actually calculating, we are trying to get the details regarding the RHP poles. So that's why Nyquist is very strong and the advantage of the Nyquist plot. Is this clear, everyone? If you have any doubts, I will try to re-explain, but if this is clear, we'll solve another problem. Revan says yes, sir. Okay. What about others? Yes, sir. Okay. Now let us plot it. One disadvantage in the MATLAB is if things are going to infinite, it will not plot because the value is so much, it will not plot. So anything which is at infinite will not be shown. So MATLAB will only show this wing as well as this wing, not the other things which are going to infinite and coming from infinite. So whenever you plot anything in the MATLAB, keep this in mind, right? Only it will show the finite values. Infinite lobes it will not show. We have to extrapolate. So it will show only this plot, this one in the second quadrant, one in the third quadrant, not the first and fourth, because they're at the infinite. It is coming from infinite circle. It is like an infinite circle. So my Nyquist stability criterion is k by s into s plus 1. Say let us take k equals to 1. Then k by s into s plus 1, right? So s star s plus 1. So 1 by 1 plus s. So if you see, it is coming from 0 and then it is going to infinite. It is coming from 0 and then it is going to infinite. And from infinite, it is having a big circle and coming all the way there. But because it is going to infinite, it is not showing the value. But if you see the direction, it is going from here to infinite and then from infinite to all the way to right side infinite and right side infinite to negative side infinite, and then it is coming here. So this is the overall Nyquist plot. But as I said, these infinite points will not be shown because they are infinite. So these infinite lobes will not be shown in the MATLAB. So that is the bottleneck, but we are trying to get the overall understanding. Is this clear, everyone? Okay, yes, sir. Now we'll solve another such interesting problem, but it has two zeros at the origin. So what difference does it make? 1 0 2 0. It is very clear. If I have 1 0, it is epsilon e to the power j theta. If it is two zeros, it will be 2 epsilon e to the power j 2 theta. So it is corresponding to double angle that can alter our Nyquist plot. So let us see how it is going to change. So I'm considering two examples for Nyquist. Once it is done, let us shift to Bode plot. Bode plot, I have considered again two examples, but let us see. Again, I'll try to draw the contour. I'm considering the. In the meantime, can you tell me how many RHP poles are there in this problem? So here we are taking one small circle, then infinite circle. Anyone, how many RHP zeros? In the meantime, I'll consider. So this is 0 angle minus 90 degrees. This is 0 angle 0 degrees. This is 0 angle 90 degrees. This is infinite angle 90 degrees. If I make any mistake, kindly let me know. Infinite angle 0 degrees. This is infinite angle minus 90 degrees. So let us call this point 1, same, point 2, point 3, point 4, point 5, point 6. And then we are asked to draw the Nyquist plot. Okay, I'm considering real as well as imaginary. And then my point of interest is -1. Let us see if it encloses -1. So this is my -1. And this is my real axis and this is my imaginary axis. So this is real, this is imaginary. So I'll now again traverse from 1, 2, 3, 4, 5, 6 and I'll draw and I'll say how many times it is enclosing -1. So here things can get tricky. So let me check the answer. So Ramesh says 0 poles, 0 on RHP, Nagarkar, Swamini, and then 0 RHP. Very good. So there are no poles on the RHP side. So in our n equal to p minus z, n equal to p minus z, we can say our p is equals to 0. So now we have to calculate n, that will give us 0. Zeros of 1 plus g of s h of s is closed loop poles of the system. So that has to be in your mind. Why we are calculating zeros? The zeros of the denominator are poles of the overall transfer function. So they are corresponding to the closed loop poles. So as I have said, first I'll start from 1, 2, 3. So for 1, 2, 3, 1, 2, and 3, we'll consider same epsilon into e to the power j theta. So let us calculate 1 by k by epsilon square e to the power j theta square means k by epsilon square into e to the power j 2 theta. Then we have epsilon into e to the power j theta plus 3. And similar to the previous problem, this will become 0. Now, if you calculate, then we'll get k by epsilon square into e to the power minus j 2 theta. So you can see, right, in the previous case, it is k by epsilon e to the power minus j theta. Now it is contributing to 2, double the phase. So that can change the stability of the system. So let us find it. So now this is my epsilon e to the power j theta that I am calculating, and corresponding whatever gain, angle, phase, whatever I'm calculating. So I'll start with point 1, then I'll move to point 2, then I'll move to point 3. So point 1 is what? 0 angle 90 degrees. So 0 angle minus 90 degrees, then 0 angle 0 degrees, then 0 angle plus 90 degrees. So can you tell me what will be the gain and phase for each of that? You have to calculate k by epsilon square e to the power minus j2 theta. So here things can get really tricky. We have to, a little bit have some conscious. Once we do that, it is simple. Anyone? Any idea? So for 0 angle minus 90 degrees, what will be the gain and what will be the phase? So if we substitute 0, epsilon 0, k by epsilon square will become infinite. And if I substitute theta to be minus 90 degrees, then it will be gain will be infinite. Yeah, Raman says gain infinite, and angle will be minus of minus 90 degrees plus 180 degrees into 2, right? So that's why it will be infinite angle 180 degrees. This will be infinite angle 0 degrees. This will be infinite angle minus 180 degrees. So minus 180 and 180 seems to be on the same point, but what I will do is, instead of minus 90, I'll consider minus 70, which means angle will be 140. So it is in the quadrant 2, right? So this is in quadrant 2. This is in quadrant 3. Because if I consider plus 70 degrees, it will correspond to minus 40 degrees, which means it is in quadrant 3. So that is very clear. So point 1 is in the quadrant 2. So it is at infinite. So my point is somewhere here. Okay, this is my point 1. And then my point 2 is infinite angle 0. So it is infinite angle 0 here. So this is my point 2. And then my point 3 is somewhere here. It is in the third quadrant, because it is very important whether they are overlapping or not. So that's why I have considered that. Whereas in the previous case, even if you consider angle to be 70, 60, 50, magnitude is 0. So it is very close to the origin. So it doesn't matter. But here the magnitude is infinite. So the angle, if it is in the quadrant 2, it can fully change the quadrant, and then it can mean different thing. But however, if it is in the origin, it is around the origin. Even if it is Q2, Q1, it is very close. So it doesn't matter. But here it can change the thing. So that's why which quadrant is important. So I don't know which quadrant. So I have considered something less than 90. Minus 70 corresponds to 140. So quadrant 2. Similarly, point 3. If I consider plus 70, minus 40 corresponds to quadrant 3. Is that clear, everyone? This is very important. Now, how are we moving from point 1 to 2 to 3? So point 1 from 1 to 2, from 2 to 3. So this is how we are going. Point 1, 2, and then 3. Clear? Clear, sir. Okay. Now let us check the bigger circle, infinite angle 90 degrees. So 4, 5, 6 points. 4, 5, 6. R angle e to the power j theta. R angle e to the power j theta. So now again it will be the same, but here 3 will be ignored. So I will directly write k by, here we'll have s cube, right? It will become k by s cube. So it will be k by r into e to the power j theta whole cube. So now if you see, we got k by r cube into e to the power minus j 3 theta. Whereas in the previous case, we have double the angle, we have double angle. Here now we have triple angle. So let us see what will happen. So now I am considering here r e to the power j theta, and now I'll calculate the magnitude or gain. I'll calculate gain, angle, phase. Okay, r e to the power j theta. So first I'll start with the 0.4, then 0.5, then 0.6. So 0.4 corresponds to infinite, angle 90 degrees, infinite angle 0 degrees, infinite angle minus 90 degrees. So now what will be the gain, angle, phase? So one simple thing is the fifth case, it will be 0 angle 0 degrees, right? 0 angle 0, which is on the right side, somewhat right side. Yeah. So now tell me, for infinite angle 90 degrees, what will be the case? So someone says 0 minus 270, right? So very good, 0 minus 270. So if this is 0 minus 270 and this is 0 plus 270. So this can be also written as minus 270 is basically 90 degrees, plus 270 is basically minus 90 degrees, because I want to be in minus 180 to plus 180 to avoid any confusion. So I'm considering everything in angle, okay, minus 90, plus 90, whatever. So after 3, I have to go to 4. 4 is in 0 angle 90 degrees. So that's why the angle is very important. If you see, 0 angle 90 degrees is here. So this is my fourth point. This is my fifth point. This is my sixth point. So if I write, this is my 4, 90 degrees. This is my 5, and this is my 6. And depending upon the scaling, it might look like it will, how does it cross? Because this is infinite, right? So if it is infinite, minus 1 will be very close to the origin, right? So again, it is because of the scaling. So minus 1 will be somewhere here, very close to origin, minus 1, because this is infinite. It is very, very big. So now how are we going from 3? We are going to 4, right? And from 4 to 5, 5 to 6, and then 6 to again 1. Clear? Because I have drawn minus 1 somewhere in between, it might appear like it will cross after minus 1, but this is infinite and minus 1 is very close. So it will cross before minus 1, and then it is covering in this direction 4, 5, 6, because 4 is 0 angle minus 90, sorry, 0 angle 90, 5 is 0 angle 0, 6 is 0 angle minus 90. So that's why it is covering in this loop. So the direction here, I'll use a different color. So it is going like this, like this. So it is covering around the origin in the clockwise direction, and then again it is covering like a Pokemon, like a Pokeball. The symbol is like a Pokeball. So is this clear? Why this example is very critical? Because it has like one is this circle, one is this circle, and the angles are very close to each other, and we have to know which is in which quadrant. That is the important. If I put 1 and 3, it might look like it's a horizontal line, but it is not. It is clearly in this quadrant, it is clearly in this quadrant, and there is a crossing. So that's why it is very, very important. If you have any doubts, I'll explain again. Else, or one thing I'll do, I'll finish this problem and I'll re-explain everything. That will be matter. So if you see this inner one, yeah. So if you see how many encirclements are there, I'll use blue color. So here is one encirclement in the clockwise direction, right? So this is one encirclement, right? And then outside there is another encirclement. One is this inner one, and then another one is this outer one, right? So there are two encirclements. Everyone agree? One is the inner encirclement, one is the outer encirclement, right? Everyone agree? Two encirclements. Can you see that? Let me draw it again. So one is in the inside, one is on the outside. So it is covering one inner smaller one and one outer smaller one. Sorry, outer bigger one. So there are two encirclements. Revant and Ramesh says yes, sir. So now comes the critical point. So I can see two clockwise encirclements. Two clockwise encirclements. So now I'll go back to my original equation and I'll see what is the condition. So my n is equals to p minus z, and here it is given encirclements in counterclockwise direction. So if I am saying there are two clockwise encirclements, it means there are there are minus two counterclockwise encirclements because they are opposite. So this is very important. Direction is very, very important. So I will get n equal to minus 2, not 2. N is equals to minus 2. So now if I do n equal to p minus z, my n is minus 2, p is 0. So what will be the z? So n is equal to p minus z. Minus 2 is equals to 0 minus z. So z is equals to 2. So we can see that 1 plus gh has two RHP zeros, which means the closed loop transfer function has two RHP poles. So the system is unstable. So this is two RHP poles. So the system is unstable. So just by adding one S term in the denominator, the Nyquist plot has entirely changed, structure has changed, and then there are two RHP poles on the right side and the system is unstable. So one S term can make this much difference. So that's why I have considered this example. So let me quickly explain. Then if you have any doubts, I'll try to explain again if you have any doubts. So I have considered g of s equals to k by s square into s plus 3. So excluding this pole at the origin, I have to consider the RHP side. So I have one small circle, one large circle, and this is how I'm going in the clockwise direction, which is important. We are always moving in the clockwise direction. So if I'm moving in the clockwise direction, first I have considered small one, which is epsilon e to the power j theta. And for 0.123, I have gotten this. And quadrant is very important. If you are not sure about the quadrant, don't take 90. Take less than 90, 60, 70. If I take 70 minus 70, it is 140. So quadrant 2. If I take plus 70, it is coming minus 140, which means quadrant 3. So then I have put 1, 2, and 3, and I have gone from 1 to 2, 2 to 3. Now 4, 5, 6 are little bit tricky, but still easy. So 4, 5, 6 is the bigger circle. Infinite angle 90, infinite angle 0, infinite angle minus 90. If I am doing that, I am getting 0 angle 90, 0 angle 0, 0 angle minus 90. So first thing I have to do is I have to put the dots, and then I have to go from 3 to 4, 4 to 5, 5 to 6, and 6 to 1. So now I can see there is one clockwise encirclement in the inside smaller circle, and then one clockwise encirclement in the outside bigger circle. So there are two clockwise encirclements which means there are minus 2 counterclockwise encirclements. So n is minus 2. So if I substitute z equals to 2, so z will always say that 2, z will always say RHP poles, right? RHP poles of the closed loop system. So z can never be negative. If z coming negative means you have made a mistake, which will give you another chance to cross check. So z will either be 0, which means 0 RHP poles, or a positive number, which means positive number of RHP poles. So either z can be 0, which means stable system, or z can be positive integer, which means unstable system. So these things you have to keep in mind. Apart from that, the process remains the same. One is if inner circle is not there, I can directly substitute 0. So if there is no s square, I have k by s plus 3. So I'll directly substitute s equals to 0. I'll get k by 3. Simple and straightforward. K by 3 means it is on the real axis. K by 3 angle 0. Only when there is a pole on the imaginary axis, it will make your life difficult. So that's why I have considered two examples, which has pole on the origin. So if you have any doubts, you can ask. Else now we can move to the Bode plots. Any doubts, anyone? Ravan says no, sir. Okay, if you don't have any doubts, if you have any doubts, you can mention in the chat box. If you don't have any, I'll quickly plot it. So instead of s, we have s square in the denominator, and s plus 1 has become s plus 3. So let me run and then see 1 by s square into s plus 3. Again, whatever I have said, the same thing that you have to keep in mind. It will only give that is closer to the origin. It will not give anything that is infinite. So this might be also at infinite, so that's why it is not giving. So it is going in this direction, but sometimes the MATLAB will not give the actual plot, so you will miss most of the things, like in this case where it has not given the entire picture and it can be difficult. So that's why sometimes it is okay to follow MATLAB, sometimes it will not give the entire picture. So that's why if you see in sir's lecture, sir has drawn externally, not the MATLAB plot, he has drawn externally. Yeah. So that being said, there is less than a minute. If this meeting ends, kindly join back. Once you are back, we can start Bode plots. If you have any questions, until then you can ask me. Yeah. So now you can go back and check in sir's lecture that sir has externally drawn. It has not given by Bode plot, I mean MATLAB plot. Any doubts? So any doubts until this point? If not, we can go to Bode plot. Okay, I assume no doubts. So again, why we are considering Bode plots? So Nyquist plot, if you see, things can become very complicated, like this crossing around this, how it is moving. Again, it is a small, like third order function. What if I have s to the power n into s plus 3 into s plus 5 into s plus 4? It is very complicated. What if it has multiple crossing in the real axis? How do I know? How do I exactly know how many times it is encircling? Because here we have considered standard examples. What if the order has increased? What if there are zeros? Okay, and what if things get complicated? We might not be able to get the entire Nyquist plot hand drawn. It becomes very difficult. So that's where you can draw the Bode plot. But Bode plot cannot always give the stability criterion. Nyquist is strong that it can give the stability accurately in every case. But Bode plot it cannot always do, especially when it has RHP poles as well as if it's a minimal phase system. So still, we'll try to understand Bode plots in majority of the cases. Whatever systems we have, Bode plot will do the work. And also we'll be using this Bode plot to design the PID controller in the upcoming session. So there it will help us to understand and visualize. It is much simpler than Nyquist. So that is one. It is simpler and easier to draw compared to the Nyquist plot. So in that case, it is helpful, but it cannot always give us the stability information. So in that case, that is the drawback of the Bode plot. Again, as I have mentioned, I would be very happy to teach in detail, but because we are limited time, I have to cover. I'll just consider few examples and draw the Bode plot, and then we'll solve few problems, and then we'll compare with the MATLAB. So in this case, I would like to spend more time in the MATLAB because it would be easy for me to teach from the MATLAB. But again, we can always draw and then compare with it. So if I have say g of s is equals to, again here we'll have magnitude plot and phase plot separate. In the Nyquist we have everything together. So if I say g of s is equals to some constant, say 10, then magnitude is again in dB. So if I am talking about magnitude of gj omega, it will be 20 log 10. So it is a constant, and phase gj omega is 0. Here the plot is logarithmic, so x-axis is logarithmic, so 20 log 10. So if I consider this, say this is my mod gj omega and this is my omega, so it is always constant. So it is constant, which is 20 log 10. And if we draw the phase is always at 0. So if I'm drawing the phase, so omega is in logarithmic scale. So this is gj omega angle. It is always at 0 degrees. This is for constant. It can't be negative constant because log of negative doesn't exist. So keep that in mind. Now if I consider, sorry. So now if I consider first order system, or let me consider one example. So if I consider g of s to be some constant, say 1 by s. Now angle gj omega mod gj omega will be 20 log 1 by j omega. So it is mod j omega, right? So it is minus 20 log omega. Because I am plotting with respect to log omega, not omega. So it has a constant slope. So if I am considering this, this is basically logarithmic. Okay, it is log. So that's why x-axis is kind of log omega, not omega. So y-axis is mod gj omega and x-axis is log omega. So it has minus 20 as the slope. So we'll get something like this. It is falling minus 20 dB per decade. So this is minus 20 dB per decade. And if you calculate the angle gj omega is minus 90 degrees, because 90 degrees in the numerator corresponds to 90 degrees in the denominator corresponds to minus 90 degrees. So it is something like that. If we again plot the phase, we'll get minus 90 degrees. This is minus 90 degrees. Okay. So I would like to consider this not there. Say here, I'll consider here. Why, I'll tell you. Okay. So now if I consider instead of g of s, if I'm considering s, right? So then it will become 20 log omega. So it will be increasing with 20 dB per decade. So I'll also plot that. So in that case, it will be increasing with 20 dB per decade. I am using the same plot so that we can compare 20 dB per decade. I think this also I'll use the same color so that you can. So this is going at 20 dB per decade. Similarly, here angle will be plus 90 degrees. So it will be plus 90. I'm just trying to explain both the examples in the same so that it will be easy to correlate. So one is 1 by s, one is for s. So if I mark that, this is for 1 by s, and this is also for 1 by s, and this is for s, and this is also for s. So is this clear until this point? If you have any doubts, please stop me at that instant. Raven says yes. Okay, now let us go for first order. 1 by s instead of 1 by s. What if I have g of s again? I'll take two examples. One is 1 by s plus a. The other one is s plus a. So how does it look? So I'm not again deriving. I'll just show how it looks. Just to save time so that we can spend on something useful. So we have magnitude plot, something like this. So instead of like it will start red color, it will have some magnitude, and then at a it will increase. Okay, so this is 1 by s plus a. I think I should normalize it. That way it will be better. So instead of this, I'll consider something like this. Because the magnitude should be same. So 1 by 1 plus s by a, and this is 1 plus s by a. So at omega equals to 0, the magnitude is same for both. So this will be 1 plus 1 by s by a. 1 by 1 plus S by A, and this is the magnitude. So we have omega. This is mod Gj omega. And here also this is angle Gj omega. Okay. So angle Gj omega. So now the other one will be, how to draw the dotted line. Okay, it is not there. Then I'll draw a hand drawn. So other one also will start at the same point and then it will drop. Sorry, my bad. I have drawn the opposite. So pole will go down and then 0 will go up. Sorry for that. So pole will drop with minus 20 dB per decade, and then 0 will increase with plus 20 dB per decade. So both will have the same points. So this is 0, which is going with 20 dB per decade, and then this is pole, which is going with minus 20 dB per decade. If we draw the phase as well, let me scroll down. So if we draw the phase as well, both will start at 0. One will go to plus 90, one will go to minus 90. So this is angle Gj omega. So it will start at 0. And this is the frequency, right, that we are talking about, A. So here also A. So at A exactly it will be 45. Before that, okay, and this will go in the same way. Okay, so basically this is plus, each 0 correspond to plus 90 degrees and each pole corresponds to minus 90 degrees. And then at exactly A, this will have 45 degrees. This will have minus 90 degrees. And similar to the gain, it has plus 45 degrees per decade, and this will have minus 45 degrees per decade slope. This is the slope. So for first order, if it is a pole, it is going down. If it's a 0, it is increasing. And then the phase also at A, it will be 45 degrees. So 1 decade before it will start increasing, and 1 decade later it will touch the 90 degrees. So it is increasing at 45 degrees per decade. So it will take it 2 decades to go from 0 to 90. Similarly, same story from 0 to minus 90. Is this clear? Maybe I'm going a little bit fast, but just to cover like the concept in the time. Is that clear? Okay, I'll meantime show, if you have any doubts, you just mention. If you don't have any doubts, I'll just consider the first order Bode plot. So here I have considered 1 by 1 plus s by 1, 1 by 1 plus s by 10, 1 by 1 plus s by 100. So basically I'm shifting the A, 1 is at 1, 1 is at 10, 1 is at 100. So they'll start falling at different frequencies. Okay, let us check. So someone has mentioned, Revant. Yes, sir. So I guess no doubts. Sir, can you explain one more the phase representation? Okay, okay. Yeah. So G of J omega, if you consider S to be 0, it will be angle will be 0. If you consider S to be infinite, it will be angle will be tan inverse infinite minus 90 degrees. Similarly here tan inverse infinite plus 90 degrees. So it will start from 0, it will reach to plus 90, it will reach to minus 90. But if you consider at A, if you consider S equal to J into A, it will be 1 plus J in the denominator, means 45 degrees. It will go to minus 45. It will also go to plus 45. So at A, it has 45 degrees. And then the Bode plot says that the angle will increase at 45 degrees per decade. So approximately at 1 by, so if this is A, approximately at A by 10, the angle is 0. And then approximately at 10A, the angle is 90 degrees. So the phase is also increasing linearly at 45 degrees per decade in the case of 0, and minus 45 degrees per decade in the case of uh, pole, and then it will settle at minus 90 degrees. So it will start from 0 degrees and then it will end at minus 90 degrees in the case of pole, whereas in the case of 0 it will settle at 90 degrees. So this is what Bode plot will teach us, and derivations I have skipped again for the sake of saving time. But if you calculate omega tending to 0, omega equal to a, and then omega tending to infinite, you will get 3 points, and then Bode plot will draw using straight lines. But the actual Bode plot will have a little bit curvy nature whenever it is increasing, whenever it is decreasing. But this is asymptotic Bode plot. So we'll draw the straight lines, which will give very accurate value near the what do you call that point. So now using this knowledge, we'll be able to draw the Bode plot for multiple such. If I have a big transfer function, again because it is logarithmic, right? So if I have a transfer function which is a multiple of 2 to 3 transfer functions, it means I will draw the Bode plot individually and then I'll add them. So that is the overall understanding of the Bode plot. Because since it is logarithmic, anything that is in product will become addition. So that we'll see once we solve the problem. Yeah. So is that clear? Whoever was asking, Revant? Yes, sir. Okay. So now let us see the Bode plot. So G1 is at 1. So 10 to the power 0 is 1. So it will start dropping from 1. This will start dropping at 10. This will start dropping at 100. So in this way, I can see again, as I said, our Bode plot is asymptotic approximation. So we draw straight lines, but in the actual it will be curvy. So it will start from 0 and it will end at minus 90 degrees. So depending upon let me go back here where I am considering this 1 s by 1, s by 10, s by 100, it will start falling from that frequency. So if I don't consider 1 by, and if I consider only 0, so 1 plus s by 1, 1 plus s by 10, 1 plus s by 100, it is 0, so it should increase. So let us see. Yeah. So if you see, it is going up, and then angle is also going from 0 to 90. So this is 0 to going from 0 to, it will increase at 20 dB per decade. This also will increase, but it will start at 10. This will start at 1, 10, and 100. So if we consider the three examples that we have solved, so let me take gain 10, and the first example be 1 by s by 10, and the second example is 1 plus s by 10. So I have considered one constant. I have considered one pole at 10, one 0 at 10. So let us see how it is going. What happened? 1 by 1 plus s by 10, 1 plus s by 10. Extra legend entries G1, G2, G3. Okay. This is 10. Why is it not showing? I think 10 has some issue. Let us 1 by 1 plus s by 10, 1 plus s by 10. Say let this be 1 by s, the other example that we have considered. Yeah. So first one is 1 by s, which is, directly coming like this. And then the angle is minus 90 degrees, which is what we are also considering here. 1 by s, it is flowing down, and then angle is minus 90 degrees. If you consider the second one, which is the 0, it is going up 0 to plus 90 and the magnitude is increasing. If you consider the pole, it is flowing down from 10 magnitude and it is going from 0 to minus 90 degrees. So in this way, we can draw the asymptotic Bode plots and also cross check with the MATLAB whether what we are drawing is right or wrong. Again, I'll give this plot, Bode plot to you so that you can cross check. This is just to explain, we have defined the transfer function s, and then we are giving the transfer function. This is just Bode options, and then this is the Bode plot command, and I'm changing the text to Times New Roman with font size 24. So these are like just to make the plot look nice, but h equal to Bode plot of this should be fine. And once you run, it will plot all three, and it will also give this legend. So depending upon different transfer functions, I can get the Bode plots and compare whether what we have drawn is right or wrong. Is that clear? Yes, sir. Okay. Now, if I go to second order, This is first order, right? If I have two such poles, it will start dropping at minus 20 dB and again minus 20 dB. So eventually it will go to minus 40 dB. Now if I solve, if I consider another one, say g of s is equals to 1 by 1 plus 2 zeta s by omega n plus s square by omega n square. Similarly, here I will consider 1 plus 2 zeta s by omega n plus s square by omega n square. So because now it is second order, the uh, slope will become double. Okay, so sorry. So what I will do is I will consider this example only, and then I'll redraw it easily so that we can correlate. So now the frequency is omega n. So this will be omega n, and now it will drop at minus 40 dB per decade. Okay, minus 40 because there are two poles there, minus 40 dB per decade. And similarly, this will go up with plus 40 dB per decade. This will be plus, sorry, this will be plus 40 dB per decade. Similarly, the angle will now go from 0 to 180 because there are two poles, right, and two zeros. So the angle will now move from 0 to 180 degrees, 0 to 180 degrees, oh, sorry, 0 to 180 degrees. And then this will go to minus 180 degrees. And because the angle has doubled, slope will also be double. Instead of 45 degrees per decade, we'll now have plus 90 and minus 90 degrees per decade. Here also plus 90 degrees per decade. So it is just to correlate, I have considered the Bode plot like this. But actually, depending upon zeta, there can be a peaking behavior. So the peaking behavior can be, instead of this, it can have something like this, or it can also have something like this. Similarly, for this case, zero case, there can be dip like this, a bigger dip, or no dip at all. This can be possible depending upon the zeta. Similarly, angle can be something like this, or it can be sharper, or it can be very sharp. I'll show this using MATLAB because that will be better. Similarly, for this, the angle can be smooth. So the angle can be smooth, something like this, or it can be sharp, or it can be intermediate also. Let us see one example. What I mean to say, our asymptotic Bode plot says that it is just two straight lines, but depending upon the zeta, there can be peaking behavior. There will be a peak. So what is that peak? Whether, how to see, I'll consider another MATLAB simulation case study for second order Bode plot. So here I have considered 1 plus 2 zeta s by omega n plus s square by omega n square. So my omega n is 100. 1e2 means 100. So if I plot this, 1e2 is basically 100. And then 1e4 is nothing but 10,000. Okay, 10,000. And eta I have considered 0 0.1, 0 0.3, 0 0.5, 0 0.7, 0.9, 1, 2, and 10, and see how it is changing. So if I have done the same thing, I am just increase the transfer functions. So if I am doing this, you can see for G1, which has low eta, it has peaking behavior. But as zeta is increasing, the peaking behavior disappears. But if you see, it is now falling at minus 40 dB per decade, and the angle starts from 0 and it will go to minus 180 degrees. So in the same way, if I consider 0, it will be the mirror image, not mirror image, water image. It will be above. And if you see, depending upon the zeta, it can be very sharp. So it can go slowly or it can go very sharp depending upon the zeta. So if I remove this one, then it becomes 0. Now two poles are there, right? Now let me consider two zeros. So now everything has to go up. So there will be a dip. So now if you see, it is just the water image inverting. So whatever is there in the bottom, now in the top has become bottom, and now it is increasing 40 dB per decade, and the angle is going from 0 to plus 180 degrees. So this is how it is there. I'll give you this code so you can play around and then try to understand and correlate that. But I have written the code a priori so that it will save some time. Is that clear? Yes, sir, clear. Okay. Now this Bode plot. So how do you do? So when you have multiple transfer functions, right? What you will do is first you have to normalize everything. So I will have g of s is equals to 10 into, first I'll remove 20 into 1 plus s by 20 by 5 into 1 plus s by 5 into 2500 into 1 plus s by 50 plus s square by 50 square. Okay. Now let us separate the gain aside. So 10 into 20 is 200 by 5 into 2500. So let me use this. So 10 into 20 by 5 into 2500. 5 into 2500. So it is 0.016. So I can write it as my g of s is equals to 0.016 multiplied by 1 plus s by 20 multiplied by 1 plus s by 5 multiplied by 1 by 1 plus s square by 50 square, right? It is 2 zeta into omega n. So zeta is 0.5. I can consider it as 2 into 0.5 into zeta omega s by omega n plus s square by 50 square. So if you do this and then individually plot the Bode plot, okay? And then add it up everything. So let us do the same thing a little bit deeply. So I have it here. I have this image, this axis here. So I'm basically drawing the magnitude plot. So this is mod gj omega, and this is omega frequency. So 0.016 is 20 log will be some very negative value. So it will be somewhere here. So the first transfer function will have some negative value. It will be somewhere here. Okay. And then 1 plus s by 20, it will start dropping from 20. So if I consider this as 20, then it will be something like this, right? It will start from 0 and then it will start falling. 1 plus s by 5, it will start raising at 5 itself. So it will be, I'll use a light color, light green. So it will come from here and then it will increase. Okay. And then this occurs at 50. So this will occur at 50. So this is my, sorry. So this is my 50 and then it will start like this and then it will drop 40 dB per decade, right? So now what we are going to do is we are starting from the beginning and we'll keep on adding. So this is where things will get very interesting. So I will start from 0. Then 1 plus s by 5, what it will do? Sorry, this is s plus 5 is in the denominator, s plus 20 is in the numerator. My bad, I have messed up. So s plus 5 has inverse, right? It is in the denominator, so it will act like a pole. So this will act like a pole. This has inverse. So what happens is this this will be deleted. This will also be deleted. So at s plus 5, it will start to fall. And then at s plus 20, it will tend to increase. So now if we combine both, so at 0, we have this blue line. Then at s plus 5, we will start to fall, right? So we'll start to fall until s plus 20. And then this minus 20 dB, this plus 20 dB will be equal. So then it will become 0 because both will get cancelled out. And then once we reach 50, then we'll start falling at minus 40 dB per decade. Is this clear? Basically, we have to draw everything individually and then we have to go and then see these two are added. So minus 20 dB per decade. Here, these and this will get cancelled out. Again, it will become constant. Again, here it is minus 40 dB per decade. So it will drop at minus 40 dB per decade. Similarly, we have to draw the phase. So 0.016 doesn't have any phase. So 5, 20, and then 50. Let us draw the phase also real quick and then we can cross check. So omega, this is a phase. So we have 5, then we have 20, and then we have 50. So scaling might be here and there. So what does phi correspond? Phi corresponds to pole, right? So pole means it will have some angle like this, and then it will start falling at minus 50 dB per decade, but it will have a decade time, right? So it will reach minus 90 degrees at 50 because I have said it will take 1 decade after that pole to reach 90 degrees and it will start from 0.5. So it will start from 0.5 and at minus 50 it will reach minus 90 degrees. Whereas the 20, it will start from 2 and at 200 it will reach 90 degrees. So it will start at 2. This guy will start at 2 somewhere here and then it minus plus 45 degrees and then after reaching 200 then it will settle. Whereas this 50 guy, he will start from 5 and then at 500 he will reach. So this 50 guy will start from 5 and then he will fall at a faster rate and then at 500 he will reach to this point. So phase sometimes can be little cumbersome, but because I did it in a hurry, I have expanded the scale. But the objective is to draw each and every Bode plot step by step and then add one on top of each other and then go with the summation plot. So from here, then it will follow green and then how it is following. So if you draw the Bode plot clearly individually, then it will become very easy. So the logic is simple. We have to follow this logic and then this is a by 10, this is 10a. So I did it in a hurry, but ideally we have to consider 5, 0.5, 50 for 20, 2 and 200 for 50, 5 and 500. Then it makes more sense and then we can get the plot quickly. So just to show how the plot will look like, let me consider this transfer function and then let me plot. So I have one Bode plot also where you can consider 10 into s plus 20. So 10 star s plus 20 divided by denominator we have s plus 5 star s square plus 50s plus 2500. So if I plot, initially it is starting from a negative value. If you see it is starting from a negative value, then it is falling and then it is constant for some time. Then it is falling and then almost constant for some time and then it is falling at a faster rate. Whereas phase, it is little bit smoother, but if you see both are kind of following each other. So once you draw this Bode plot clearly with all the numbers and then properly draw, then it will be making more sense. But because I have done it little bit hurry to finish within the time, I have done little bit hurry. But the objective is clear, right? You have to draw the Bode plot of each and every function individually and then sum it up. So there is less than a minute. This meeting might end and I guess you might have few questions. You can ask if this meeting ends, kindly join back so that we can discuss and end this session here. So any questions? Okay, so if you don't have any questions, then I can end this session here. Thank you for joining and making it interactive, and I wish you all the best. See you again on next Monday. In that case, I'll end this session. Good night, everyone.